All right, so today we have two new types of problems to solve using our linear systems. There are mixture problems and then there's distance, speed, time problems. Both are science related. One is chemistry, one is physics, that kind of thing. So if you can see all the data in these mixture problems and just create everything you need to create in terms of the equations, these problems are actually extremely similar to our investment problems from the previous lesson. Now, that being said, sometimes it's hard to pull out the data and really kind of wrap your head around things. So I'm going to show you a visual trick after we solve the first problem in order to help you create the equations, which may make your life just a little bit easier. So let's try this one first of all. So we start off and we have Jeff has a bottle of 5% acetic acid. Remember, we always want to rewrite our percentages as decimal places. So that one's going to be 0.05. This one's going to be 0.1. This one down here is going to be 0.08. So let's reread the problem again. So Jeff has a bottle of 5% acetic acid and a bottle of 10% acetic acid. How much of each should he use to make 250 milliliters of 8% acetic acid? So basically he's got 5% and 10%. He's going to combine them together in certain quantities, and that's going to come out at something that is 8%. So obviously, the 5% is going to lower the percentage of the 10% to bring it down to that 8%. So how does this actually work? Well, if you read the problem, it tells you exactly what your unknowns are. How much of each should he use? That's our unknown. So we can just say, let's let X represent the amount of 5% acetic acid, the amount of 5% acetic acid, and Y is going to be the amount of 10%. Now, the astute ones of you are going to look at this and say, hey, this is exactly the same as those investment problems. I don't see any difference at all. So now we got to try and pull out the information here. What equations can we come up with? Well, we know that he's making 250 milliliters of solution. So we got a total. So that means if we add up the two amounts, we get that total. So that's our first equation. Equation number one is just going to be X plus Y is equal to 250. 250 what? 250 milliliters. Okay, we know that 250 milliliters has an 8% acetic solution. So what are we really saying? We're saying that if I take a certain amount of substance X, a certain amount of acetic acid that is 5%. So equation 2 is we're going to take that percentage and multiply it by this amount. How much do I have? And it's a 5% solution. So let me just kind of fix that a little bit. Getting rid of all my stuff here. It's not getting rid of those ones. That's not fun. Whatever. So it's going to be equation 2. And we have 0.05x plus the 10% solution. How much of it? Whatever. That's what we're trying to figure out. So 10% solution, 0.1 y. And when we combine those two together, we get an 8% solution. And how much of it? 250 milliliters of it. We know exactly what we got there. We got 250 milliliters of 8% solution. Okay, so we can simplify this by doing that math, of course. And if you take 0.08 and multiply it by 250, yep, that's right. Just give me 1 second. Just need to pause for 1 second. There we go. Sorry, just had to check my numbers here. So what we want to do is we want to, of course, use substitution or elimination. And the easiest thing to do in this case would be, let's get some of the values to line up and make sure that we can use, in this case, elimination. So I could multiply the whole thing by 100, and that would get that 0.05 up to a 1. Or I could just multiply everything by 10 and bring this 0.1 up to a 1. And then the y's would match. So let's do that. So let's take equation number 2. Let's make equation number 3 by multiplying equation number 2 by 10. So 0.05 becomes 0.5x plus 0.1 is just 1, so that's just y, is equal to, now we're going to move the decimal place over here. So this 0.08 becomes 0.8. Well, that's the same thing as 80%. 80% of 250 is 200. Okay, so we have equation 1 and 3 that we're working with. So let's use these two things together, and we're going to subtract them. So we're going to say, why are we subtracting? Because we're getting rid of the coefficient in front of y, which is just a 1, and they have the same sign, so we have to subtract. So we're going to say 1 subtract 3. So that's saying x plus y is equal to 250, and that is we're going to subtract 0.05x. Oh, I made a mistake. It's 0.5. My mistake. I don't know why it doesn't let me erase that whole thing, but I guess we'll just have to work for it. 0.5x, there we go, plus y is equal to 200. And now we're going to subtract these guys. So 1 minus 0.5 is 0.5. And 1 minus 1, that's 0, so that's gone, equals 250 minus 200, that's just 50. So when I divide both sides by 0.5, I get x is equal to 100. What does that tell us? Well, let's look at our original problem. What does x represent? It represents the amount of 5% acetic acid. That means we used 100 milliliters of 5% acetic acid. So let's substitute this guy back in. Sub x into choose an equation. In this case, equation 1, again, is the easiest. And we're going to try and find y. It should be nice and straightforward. So we end up with x, which is just 100, 100 plus y is equal to 250. Now when we bring the 100 to the other side, we end up with y is equal to 150, which makes perfect sense. So therefore, 100 milliliters of 5% acid and 150 milliliters of 10% acid were used. Okay, so mathematically that should actually work if you ever had to do that in science class. So this is the idea of you having to look through the problem and pull out the data. Is there an easier way? Well, there can be. So I'm going to try and put this together for you in a graphical kind of table. And what I'm saying is, for all of these mixture problems, you can use this exact same table and apply it over and over and over again, and you should get the correct results each time. So I'm going to scroll down a little bit. So generically, what does the table look like? So what I want to do is I want to create a table that has 2 rows and 3 columns. Where did my mouse go? There it is. So 2 rows and 3 columns. We'll leave it as black. I'll do it generically up here, and then we'll do it in the question itself. So what should be the first row? The first row should represent the volumes of each substance. Okay? So the first row is the volumes, the amounts of each substance in whatever unit you're working with. Maybe you're working in milliliters, maybe you're working in liters. It doesn't really make a difference as long as you're consistent. And the second row is going to represent the amount of each pure substance. All right, so the pure amount. Pure substances. Okay. So actually the exact amount in that area. I'll try and explain that a little bit more clearly in a second. So what are the columns? Well, the first column is going to represent our substance A, whatever substance A is in the problem. What's going on here? There we go. I don't know why it's doing that. So let's say substance A. Every problem is different, so I'm just calling it substance A here generically. And then we have substance B. Spelled substance wrong there. Substance B. And then we have the total, the final mixture. Now, in every one of these problems, let's just draw a line here. Let's see how straight I can make this. in every single one of these problems, we're always looking for the amount of each original solution or each original substance. So that's really the goal here. And from this information, we're going to be able to pull out our equations. So let's see. What I'm looking for is every single time, since we're looking for the amount of each original solution, that means that's the volume. That's what we're actually looking for. So we want to know how much of substance A did we add and how much of substance B did we add. And when we combine those together, we get some total final mixture, let's say Z. Okay? Now, when we're talking about pure substances, I want to figure out, well, how potent is each substance, the pureness of that substance. So in this case, it's going to be our percentage. So A multiplied by X. So this is actually going to be our percentage here. Okay? And this one is going to be B multiplied by Y, and that's going to give us the total percentage of the final mixture. Now, these seem pretty generic, but these are actually our equations. So we're going to say X plus Y is going to equal to Z. We just have to know what these numbers are and fill it in. And then it's going to be AX plus BY is going to be equal to CZ. And you're like, I still don't understand, Mr. Lane. That's okay. Let's do an example so you actually see this. So a chemistry teacher needs 5 liters. There's our total. That's going to be our Z. Of 38% phosphoric acid solution. So 38%, that's 0.38 phosphoric acid solution. So that's our big C here. So that's the 38% is the C. Okay. The acid solutions available to mix are 30% phosphoric acid and 50% phosphoric acid by volume. How many liters of each solution must be mixed to make the 38% solution? Every single one of these problems is going to have the same setup. Let X represent the amount of the first substance. So let X represent the amount of 30% acid. And let's Y represent the amount of 50% acid. Great. Now let's build this table. Okay. So what is substance A? Substance A is, I don't have tons of space, so we'll do it right here. So we have our volumes first. I'll just put a V there. And then we have our pure substances here. So this is our first row. Okay. Now we're going to break this up. We got 3 columns. So substance A, that's the 30% substance. Substance B is the 50% substance. And we know the final substance is got to be 38%. Okay. Those substances, that 30, 50, and 38 are A, B, and C in our bottom row of these setups. So we know that X is the volume of the first substance. So that's just X. Y is the volume of the second substance. And when we combine them together, we get a total of, as it says in the problem, 5 liters. Okay, 5 liters. On the bottom here, well, what is the potency of the first substance? It's 30%, so 0.3x. And then the next one, it's 50%, so 0.5y. And the final substance is 0.38. And this is going to be, of our full substance. So in this case, Z, which is 5. Look, we just made our 2 equations. All we have to do is just read it from left to right, and there's our equations. No thinking involved. All we did was fill it out. So let's create our equations. Number 1, X plus Y. I don't know why I just wrote 5 there, I'll be honest. X plus Y is going to be equal to our 5 liters. Maybe that's where I wrote it. Who knows? And equation number 2. Just read it from left to right. We have 0.3 of X plus 0.5 of Y. And that's going to be equal to 0.38 of 5. Now we got to solve in the exact same way we did before. We got to find some way to get rid of something. Okay. Well, in this case, I am going to modify both equations And we're going to get rid of, let's get rid of x this time. Yeah, let's get rid of x this time. So let's modify equation 2 first to make equation 3. And we are going to get rid of x. So we're going to make them both 3x. That's going to be our goal. So in order to get equation 2 to that point, we have to multiply equation 2 by 10. Okay. So that means we get 3x here plus 5y is equal to, now we do this math, and what you're going to do when you do this, you're going to end up with 3.8 times 5, and that's going to come out to 19. I know, weird, eh? And then we have to do the next equation. So equation number 1, we're going to bring it around. This is going to be equation number 4 now. Now to get this one to 3, we got to multiply the whole equation by 3. So we end up with 3x plus 3y is going to be equal to 15. Now, this is pretty clean, so we're going to do the math right here. Hopefully we should have space. So I have the same coefficient and the same sign, so we're subtracting. So we just have 3 minus 4. Okay, so 3 minus 3 is gone. 5 minus 3 is 2y. And 19 minus 15 is equal to 4. So y is just equal to 2. Okay, now we're just going to take this number, we're going to substitute. So we're going to say substitute y into equation 1, and we're going to find x. And here we go. Where was I here? So y, wherever we see a y. So x plus 2 is equal to 5. That means x is equal to 5 minus 2, which is just 3. What does that mean? It means that we have 3 liters, because that's the unit of measure we're working with, 3 liters of the 30% solution and 2 liters of the 50% solution. So therefore, how many liters of each solution must be mixed? Therefore, 3 liters of the 30% acid and 2 liters of the 50% acid are mixed. Okay, so that's our mixture problem. So if you create that table, it's going to be pretty straightforward for you. It's going to take a little bit of practice the first time, but just remember the first row is just the original volumes and the things that we're trying to calculate. And then the second row represents just the pureness, the purity of each solution, which is really your column header of each one. And as long as you remember that, you're good. Okay, so that is our mixture, our mixture problems. Now we're going to get into our speed, distance, time problems. Now these ones are still the same idea. We're going to use a table structure again for these ones. However, the table is definitely going to look a little bit differently. And depending on the wording on the problem, these questions can look very different, even though they're still very related. So let's start off with the first one. Speed, distance, time problems. So for those of you that don't remember, if you look at the right, we have this triangle, distance over speed, time. So using this triangle, we can calculate any one of these 3 values. So d, so if I want to calculate d, that's the same thing as saying d is equal to s times t. If I want to calculate s, then that's d over t. If I want to calculate t, that's the same thing as saying d over s, hence the triangle, okay? So this is really where this triangle is coming from, but they're all really the same equations. They're just rearranged, and you already know how to do a rearranging. So if you're worried about that, you can memorize the triangle, or you can try and just try and understand that we need to rearrange the problems to get them all the time. Okay, so let's start off. A canoeist took 2 hours to travel 12 kilometers downriver. Downriver means he's going with the current, okay? So the current, the flow of the water. So a canoeist took 2 hours to travel 12 kilometers downriver. The return trip against the current took 3 hours. What was the average paddling rate of the canoeist? and what was the speed of the current. So basically, when we're talking about the paddling rate here, really it's trying to figure out, like, if you took away the speed of the water, how fast is the canoe actually moving at? That's what the paddling rate is. That's what it's talking about here. So when we're looking at these problems, first thing we need to do is really kind of define what we're talking about. So what is the unknown values? Well, it's what was the speed of the current and what was the average paddling rate of the canoe. Okay, so those are our two unknowns. It told us in the question. So let's let x be the average paddling speed. Okay, and let's what y represent the speed of the current. Alrighty, so let's look what we got here. So we're always going to build this graph here, this table, and our three columns are going to be distance, speed, and time. So we can use this information and this triangle to help us create our equations that we're going to need. So now we want to think about breaking our problem down into the two parts that represent the whole problem. In this case, we have downstream and we have upstream. So let's think about distance. How far did he go downstream? Well, he went 12 kilometers. Went 12 kilometers downstream. He returned back, so that means he also went 12 kilometers back. So that doesn't change. We also know how long it took him to take each trip. So the first time downriver took exactly 2 hours, and upriver took 3 hours. Now the speed is what we're looking for, like the speed of each component. We're trying to find the speed of the canoe, but we're also trying to find the speed of the current. Now remember what's actually happening here. If we think about this, this canoeist is traveling downstream at a certain paddling speed, but he's moving a lot faster because he also has the current with him. So if x represents his paddling speed, he's moving a little bit faster because of the current. So he's actually moving at x plus y, because the current is pushing him down the stream faster. So the downstream speed is the speed of the canoe plus the speed of the current. However, when he's coming back up, that means the current, which is still moving in the same downward direction, is now working against him. So even if his speed or her speed is x, now the current is going against them. So it's actually his canoe speed minus however fast the current is. So this one is x minus y. Okay. So how does that help us? Well, what can we do with this? Well, we want to start creating our equations. Okay. What can we want to take this information and we want to calculate or create some equation from this. So let's start off with equation number 1. If I take my time and I multiply it by my speed, I get my distance. So I could do my distance is equal to speed times time. I could do any other order, but this is going to be the easiest one because it's nothing but multiplication and there's no division. So let's not put division in there unless we have to. So distance is equal to speed times time. So I want my constant to be on the right-hand side, so I'm going to put my distance on the right-hand side. So I'm going to put my 12 right there. And what is my speed going downstream? Well, the speed downstream is x plus y, and its time is 2. So we have x plus y multiplied by 2. Well, let's multiply that 2 through, so let's distribute. So we have 2x plus 2y is equal to 12. There's equation number 1. Great. Can we reduce this? Yeah, we can. Let's shrink this down a little bit. So if I divide both sides by 2, I just end up with x plus y is equal to 6. Now equation 1 is ready to go. Let's do equation 2. Equation 2. So if this is representing equation 1 and this is representing equation 2. So it's the exact same thing. Distance is equal to speed times time. So we have x minus y multiplied by 3 this time is going to be equal to 12. We've got to multiply it through, so we end up with 3x minus 3y, because there's a minus sign there, is equal to 12. We can again reduce this by dividing both sides by 3, and we end up with x minus y is equal to 4. So we have our two equations. We have x plus y equals 6 and x minus y is equal to 4. We need to solve. Now, since we have the same coefficients for all this, we can do whatever we want. I'm going to do addition and get rid of the y's so they have opposite signs. So let's do 1 plus 2. So we have x plus y is equal to 12. And we're going to add on to that x minus y is equal to 4. We are going to add x plus x, well, that's 2x. Y plus negative y, they go away. And then we have equals 12 plus 4, which is 16. So x is equal to 8. What did we just find? We found x. So we just found the speed of the canoe. It's 8 kilometers per hour. Kilometers, we have our unit there, per hour. 8 kilometers per hour. Great. Now we need to find the speed of the current. So we're going to take this value, we're going to substitute it. Choose your favorite equation. I'm going to put it into equation number 1. So sub x into equation 1 and find y. Okay. Alrighty. So in this case, we're going to have x plus y. So this is just 8 plus y is equal to 6. Bring the 8 over to the other side. So y, I think I made a mistake somewhere. Where did I make a mistake? Let's see. We have x minus y is equals 4. X plus y is equal to 2. Or sorry, equals 6. And when we add them, we have 2x. Oh, ha. Yes, I accidentally wrote the wrong number in there. This 12 should be a 6. I went up one level here. So we got to backtrack a little bit. This is why we check. We'll just get rid of this stuff here. I don't know why it doesn't want to let me get rid of that one. But either way, this should not be a 12. That should be a 6, which means that's wrong, and so is that. So let's go back and fix this. This should be x plus y equals 6. For those of you that caught that, good job. So we have 6 plus 4 is 10. So now when we divide both sides, we get 5. That makes more sense to me now. So now when we substitute it back in, we have 5 plus y is going to be equal to, where did we go? 6. So then when we bring the 5 over to the other side, we get y is equal to just 1. So what does that tell us? So therefore, the average paddling speed was 5 kilometers per hour. And the current speed, the speed of the current, let's say current speed, was 1 kilometer per hour. There we go. That means when he's traveling downstream, he's actually traveling at 5 plus 1, which is 6 kilometers per hour. And when he's traveling upstream, he's traveling at 5 minus 1, which is 4 kilometers per hour. And that's where the difference comes in. So all of our speed, distance, time problems are going to be related back to this, but they're not always going to look the same. So let's try another one. We've got a few to look through. Okay. So this is going to be a very similar problem. So instead of a current, we're flying a plane, and we have a tailwind, which means a tailwind means that it's coming from the rear, which means it's pushing it along. Okay, so let's try and visualize this. So with a tailwind, a plane flew 960 kilometers from Edmonton to Toronto in 3 hours. The return flight against the wind took 4 hours. Find the wind speed and the speed of the plane. So we have the exact same problem again, so let's solve it in the exact same way. So first of all, our x is going to represent the speed of the plane. Let's x represent the speed of the plane. And that means y is going to be the speed of the wind. Can't really see that that's a P. There we go. The speed of the wind. So now let's break that down and figure out which way we're going. So this one is, the first direction is Edmonton to Toronto. And the other one is Toronto to Edmonton. Alrighty. So what's the distance? The distance is the same in both directions. It's 960 kilometers. That doesn't change. Great. And the time on the way there took exactly 3 hours, and the time on the way back took exactly 4 hours. So again, this is the same problem as before, which that means is if the plane is traveling without any wind at all, it would just move at x. But since it has a tailwind, that tailwind is pushing it. So that means it's getting pushed by y. So it's just x plus y. On the way back, it's moving at its normal speed x, but it's getting reduced by the speed of the wind. So this one's going to be x minus y. So now here we are with the exact same problem as before. So we want distance equals speed over time. Or sorry, distance equals speed times time. I apologize. So again, we have our 960. So let's do equation number 1. We have our 960. And that's going to be equal to, actually, let me just move that over a little bit. There we go. Let's move it over here. So that's equal to speed times time. So 3 times x plus 1. So 3 times x plus 1, or x plus y, sorry, x plus y. We multiply that through, we get 3x plus 3y is equal to 960. And yes, this does reduce, so we could bring this down to x plus y is equal to 320. So there's equation 1. Let's do equation 2. Same idea. So in this case, it equals 960 again, but this time it's 4 hours, so it's speed times time, so 4 times x minus y. So we end up with 4x minus 4y is equal to 960. And again, this one does reduce, so we end up with x minus y is equal to 240. And we have the exact same problem as last time. We can add them together to get rid of the y coefficient. And so let's do 1 plus 2. So we have x plus y is equal to 320. And we're going to add on to that x minus y is equal to 240. And again, we're adding because our signs are opposite this time. Okay. X plus x, that's 2x. Plus 1 or plus negative 1, that gives us 0. So then we have 320 plus 240. That's going to give us 560. So x is going to be equal to 280. 280 what? 280 kilometers per hour when it's traveling to Toronto. Okay, let's substitute this back in. So we're going to sub x into, let's say, equation 1. We're going to try and find y. So equation 1 is x plus y, so 280 plus y is equal to 320. So that means y is equal to 40. 40 kilometers per hour. So that means the plane moves at 280 kilometers an hour on its own, and then the wind moves at 40 kilometers per hour. So therefore, the plane speed was 280 kilometers per hour, and the wind speed was 40 kilometers per hour. Okay, so that's the last problem that's going to look exactly like that. So when we just have a tailwind or a current, so just a force kind of pushing our object in one direction and then back the reverse direction. That's one type of distance, speed, time problem we're going to see. But that's not the only one. There's more. So let's take a look at this next one. Oops, a little too far there. So in this case, we have Jean took a trip from Brownsville to Montreal, a total distance of 830 kilometers. She traveled part of the way by bus and the rest of the way by plane. The bus averaged 40 kilometers an hour and the plane averaged 50 kilometers per hour. The whole trip took 3.5 hours. How many hours did she spend traveling by bus? So you'll notice that the table is slightly different this time. So when we're dealing with a problem where we have mixed forms of transportation, or mixed forms of movement, I should say, not transportation, but mixed forms of movement, where part of it is done by one strategy and part of it is done by the other strategy, we're going to tackle the problem like this. First of all, we have to look at what we're trying to calculate. The question was, how many hours did she spend traveling by bus? Well, the only way we can do that is if we know how much she spent traveling by bus and by plane. So those are going to be our unknowns this time. So let's say let x, which is what we're actually looking for, it represent the hours spent traveling by bus. Which means y is going to be the same, but by plane. The hours spent traveling by plane. There we go. All right, so let's label our rows. So now we have, this is the bus traveling and this is the plane traveling. So how far did the bus travel? Well, the whole trip was 830 kilometers. Okay. And she traveled part of the way by bus. We're not sure how much. And the rest of the way by plane. We don't really know yet. So we're going to have to leave that alone. So what about the speed? Do we know how fast each one moves? Well, the bus averaged 40 kilometers per hour. Okay, so we know the bus speed. And the plane averaged 500 kilometers an hour. Okay, we know the plane speed. There's not really a total speed involved in this question, so that's kind of moot. It's not really useful information. What about the time? We know the whole trip took 3.5 hours. So the whole trip, the total was 3.5 hours. Well, this time is actually what we're looking for here. So this actually represents our x and our y. And our y. So that's actually one of our equations. X plus y is equal to 3.5. That's nice and easy. So if we just kind of go down this column, we get our first equation. We add and we get our equals there. So that's going to be equation number 1. So that's going to be x plus y is equal to 3.5. Well, where do we get the other equation? Where else do we have information? Well, we don't have any direct information. But you know what we do have? We have a triangle. Let's use this triangle to create another equation. Now, since the middle column isn't really useful in terms of total speed, that means we have to do something with the distance column. Well, how can I calculate distance? Well, distance is just speed times time. Oh, I know that. Speed times time. So that's 40 times x. So this is just 40x. And our plane, well, it's the same thing. This is speed times time. So 500y. Now, combined, if we add those two things together, we get 830. So we just created our second equation. Ah, this was not too bad. This one's easier than the last one, I would say. Number 2. So we have 40x plus 500y is equal to 830. Now, obviously, those numbers are not the most compatible numbers in the world. But easy enough. We could isolate either x or y and substitute. That would work perfectly fine. But elimination is probably going to be even easier here. So let's modify equation 1 to, let's say, get rid of the x variable. So that means we're going to multiply the entire equation 1 by 40. So we're going to make equation 3 over here multiply by 40. So that means we have 40x plus 40y is equal to 140. And, well, what can we do with this? We can subtract. So we have the same coefficient, but the same sign. So we're going to say, let's subtract. So 2 minus 3. 40 minus 40, gone. 500 minus 40, well, that's going to be 460y. And 830 minus 140, that's 690. So when we divide these two, we end up with y is equal to 1.5. What does that represent? It represents the hours spent. So that means that we spent on the plane 1.5 hours. So let's substitute it back in to find x. So we're going to say sub y into 1, and let's find x. Now some of you are going to say, well, what if we eliminated the y to start out with and we ended up with x? That's great. That's all the problem actually asks you to do. So in theory, you could end the problem there and just say, well, I know how much it ended, so I could say, therefore, it spent whatever hours traveling by bus. And then you wouldn't have to do this second step. But that's not what we did this time, so we have to do it. So equation 1, x plus y. So x plus 1.5 is equal to 3.5. So when we bring 1.5 to the other side, we have x is equal to 2. So we have all of our information. So therefore, Gene traveled 2 hours by bus. And just because we have the extra information, we're going to add it. And 1.5 hours by plane. So this is the second type of distance, speed, time problem we're going to see. So the first one was really traveling one direction with support and then traveling the opposite direction with opposition. In this case, we have mixed forms of traveling, so we have to create a slightly different table which takes into account total values. So let's go. We got a couple more problems. We're going to do 2 more problems and then we'll call it. So this next one is very similar to the previous one. In fact, the rest of them will be similar. So that's really the only 2 types of distance, speed, time problems we're looking at. So Tim and Sean drove a total of 670 kilometers in 8 hours. For part of the trip, they traveled at 80 kilometers an hour, and the rest of the trip, 90 kilometers an hour. How far did they drive at each speed? So the last one was how long, so time-wise. This one is how far. So the distance is actually our unknown this time, not the time. So we have to keep this in mind. So now when we create this chart, that's going to be the key point here. So let's say we have 2 parts to this trip, part A and part B. So let's say let x represent the distance traveled at 80 kilometers, because that's really what we're trying to solve here. The distance traveled at 80 kilometers per hour. And let's y be the distance traveled at 90 kilometers per hour. That almost looks like an A. So let's think about the first part of the trip. So let's call this part A. And the second part of the trip, let's call this part B. Just keep it simple. Now, again, x represents the distance traveled. Oh, that's that first distance. And y represents the distance traveled in the second part. And combined, we traveled 670 kilometers. I'm just going to erase that. I got a little overzealous on that one. So these combined equal 670 kilometers. Great. How about speed? We know the speed. We know in the first leg, the speed was 80 kilometers per hour. On the second leg, the speed was 90 kilometers per hour. Okay. What about total speed? There's no such thing as total speed in this problem. It doesn't make any sense. So we're definitely not making an equation out of that column. Let's go to the next one. Time. Do we know time? Well, we do know that it took a total of 8 hours. But do we know how much time each one went? We don't. But again, we have the triangle. So our time is equal to distance over speed. So we can create an equation to do this. So time is going to be equal to distance. Well, distance is x. And our speed is 80. So x over 80. And similarly speaking, for the second part, that'd be y over 90. So we can combine and create equations again just by going down the column. We have x plus y is equal to 670. Down here, we have the same idea. We have x over 80 plus y over 90 is going to be equal to 8. So we have our two equations. Let's go create them and then solve. So equation number 1. We have x plus y is equal to 670. Equation number 2. We have x over 80. So x over 80 plus y over 90 is equal to 8. Now, obviously, those are not great. So we need to kind of make them work. How do we want to do this? We got to choose which variable we want to get rid of. Let's say we want to get rid of y. That means we need to make both these values equal the same, right? So there's not really pretty numbers here to work with. So what we're going to do is we are going to multiply to get to the value that we actually want. So in terms of the bottom, what do we want to multiply? Let's see here. So I want to get rid of both fractions. So basically I need to find like a common multiplier for both that 80 and the 90 to kind of get rid of them. So if I multiply those two together, I get 720. So that's what I'm going to do. I'm going to multiply equation number 2 by that whole 720. So this is going to create a bit of a big number, but that's okay. So we're going to take this equation to create equation number 3. And we're going to multiply by 720. Holy smokes. So when we do 720 multiplied by x over 80, we end up actually with a nice little 9x. And similarly speaking, over here, when we do 720 multiplied by y over 90, we end up with 8y. Oh, good. And now how about 720 times 8? Well, that's not as pretty. That gives us 5,760. Okay. Equation number 1, we're going to do the same thing. This is going to create equation number 4, and we got to get to one of these values. Since we're trying to get rid of 8y, we got to multiply our entire first equation by 8. Okay, so let's do the math. So that we have 8x plus 8y is going to be equal to 8 times 670, which is 5,360. Okay, we can do this work. We have matching signs, so we need to subtract. So this is going to be 3 minus 4. Okay, so 9 minus 8, that's just x. 8 minus 8, it's gone. And over here we have 5,760 equals 5,360. Sorry, subtract 5,360, which just equals 400. Well, that's our problem. That's our solution. So x, this is the biggest simple expression ever. So x is going to be equal to 400. Let's go solve for y now. So right now we know how far they traveled at 80 kilometers per hour. But we need both because that's what the question is asking for. It says, did they drive at each speed? So they traveled 400 kilometers the first one. Let's substitute. Sub x into equation 1. And we're going to try and find y. Alrighty. So x, which is 400, plus y is 670. So y is going to be equal to 670 minus 400, which is 270. So what did we find? We found that part A, so the distance traveled at 80 kilometers was 400 kilometers an hour. Or sorry, 80 kilometers per hour was 400 kilometers. And in part B, the distance traveled at 90 kilometers per hour was 270 kilometers. So therefore, they drove 400 kilometers at 80 kilometers per hour and 270 kilometers at 90 kilometers per hour. Okay. So these questions were similar, this one and the previous one. It's just we have to understand what information we have and what information is irrelevant. Like the speed in this case was absolutely irrelevant, as it was here. But will it always be that case? Not necessarily. Depends on what we're trying to solve for. So let's do our final question of our examples here. So we have, let's go one click. Oh, whatever. Example 15. So Sarah spent 2 hours more, so this means addition, So whenever you see that more, that means it's something on top of it. 2 hours more traveling by train than she did bus. So if bus was 10, that means train was 12, for example. Okay? The train averaged 70 kilometers per hour and the bus 50 kilometers per hour. The total distance traveled was 740 kilometers. How far did she travel by bus? So again, we're looking at distance here, right? Now this one's a little bit trickier because we can look at this problem in a number of different ways. So we want to think about our train and our bus. We're going to come back to our let statements in just 1 second, okay? Now in this case, I'm actually going to fill out what I can of this before we start doing anything else. We know that by train, Sarah traveled 70 kilometers per hour, and by bus she traveled 50 kilometers per hour. And there's no combined speed again because it doesn't make any sense. We also know that she traveled a total of 740 kilometers. Okay. Now we're trying to figure out how far she traveled by bus. Now, some of you are going to want to say, you know what? I'm going to make my distance, because that's what we're looking for, equal to x and y. Oops, I don't know why I did that. Is there any undo? There is. All right. So we can do that. We can say, let's let x be distance. So x be the distance traveled by train and y be the distance traveled by bus. And that will work perfectly fine. And we'll have the exact same problem we did just 2 seconds ago where we're trying to calculate and deal with fractions. And that'll work. Now, we could do that. Alternatively, we could make the math a little simpler by making our x and y the other side of the equation. So if we let x and y represent the time, so let's say the time traveled at each one, now the distance, we can actually calculate the distance over here, which is what we're actually looking for, equal to speed times time. So now that math is a little bit simpler. So this is 70x and this is 50y. Alternatively, if we did it the other way, if we chose to say, well, let's make distance x and distance y, that would mean time would equal to our distance over our speed, right? So it would be x over 70 and y over 50. So this would be the exact same problem as we just finished, okay? And it will work. You can solve that problem. You won't run into any issues. But I want to show you a way this time so we can simplify this a little bit. So in this case, I said, well, let's just make sure that it equals the opposite one. Let's get rid of this whole thing here. One more time. There we go. So in this case, I said, let's let x and y represent the times traveled in each one. So x, you're going to represent the time traveled by train. I know it feels counterintuitive because we're looking for distance. That's okay. We can still figure this out. Time traveled by train. And y represents the time traveled by bus. All this is doing is making the math a little bit simpler to work with. You can absolutely go the other way we were a second ago and you won't have any problems as long as you don't make any mistakes. So we have our equations. So we can go down here again, pop. So we have x plus y is going to be equal to our total distance. And what about the other equation? Do we have another equation? We do. We do. Well, let's write out the one we know first. We know that equation 1 says we have 70x plus 50y. And that whole thing is going to give us 740 kilometers. Great. What other equation do we have? Well, we know time to a degree. Sarah spent 2 hours more traveling by train. What does that mean? It means that the x is really equal to y plus 2. We know that for a fact because that's what the question says. So that actually can be our second equation. So our equation number 2, is just x is equal to y plus 2. All right. So in that case, we don't need to do elimination. We can just do substitution this time because we've already isolated for x. So let's do that. Let's say sub 2 into 1, and we're going to find y. So wherever we see an x, we're going to put a y plus 2. So we have 70 multiplied by y plus 2 plus 50y is equal to 740. So 70y plus 140 plus 50y equals to 740. Now let's collect our like terms. That should be 70y, sorry. 70y plus 50y, that's 120y. Now on the other side, we have 740 minus 140 is 600. So that means y is going to be equal to 5. What does that represent? What is y? Y is the time traveled by the bus. But you know what? That's okay. We can use that and substitute it into our distance calculation. So we can say sub y into, into bus distance, because that's what we're actually trying to calculate. So bus distance, and right here it's just going to be distance is equal to 50 times y, which is just 5. So distance is equal to 250 kilometers. Therefore, Sarah traveled 250 kilometers by bus. Now, that's the end of the question, but if we scroll up to this one, they're not that far off. Not much difference in terms of work, although the math is a little bit more complicated on the right-hand side here and more potential for error, whereas over here, quite a bit more simple. So that is all of our various types of problems that we're going to learn this unit. We learned quite a few, so make sure that you prepare, you practice a lot. Don't just assume you'll be able to recognize it and do it every single time. The more you practice, the more easy it will be to recognize the type of problem sitting in front of you. So in that case, good luck.